So, whatever. It has snowed all morning.
Nonstop.
I know. And here's the thing. It's actually supposed to snow a little bit this afternoon, not a lot. Also, what happened to the varsity boys basketball team last night?
It was like last minute. They were up like 14.
I know. They're up 14-0.
And then they were down 26 to 30.
Back. All right. Here we go. Let's get rocking on this. Chemical kinetics. When you hear the word kinetics, what do you think of? Kinetic sand. Movement. Yes. Kinetic sand day. After the AP test, bring in kinetic sand. We all have a kinetic sand day. Yes.
Bro, I remember like the commercials for kinetics. You get them like every day.
Chemical kinetics is the study of the speed or rate, put a box around rate because you're going to hear rate a lot more, of chemical reactions. Nathan, those were 50 degrees and not 90, right? Oh, they were? Oh, then I owe you those points back. I couldn't tell. So I owe you like 6 or 7 points. Okay. I thought they were 50s. Okay. All chemical reactions occur at different what? Rates. Yes. For example, rusting. Rusting is a very slow, whereas, isn't that a fancy word that I put in there? Whereas. An explosion would be very fast. A rate of reaction can be determined by monitoring the change or, let's say, decrease. Because you would agree that the reactants are going to decrease over time. Yes. A decrease in reactants over time, or an increase in products. Or an increase in products over time. So the basis, so let's make a little graph of this. So here is a graph. Here is an equation. So let's say we had 2NO2 is in equilibrium. You don't know what that means yet, but we have to start talking like it. With 2NO plus O2. Notice how I drew the top arrow going one way and the bottom arrow going the other way? Things are about to get crazy next chapter. All right? Don't worry about it yet. We're getting there. What?
I thought it wasn't going to be hard.
It's not. It's not hard. So if this is my equation, I have a what type of equation rolling here? Decomposition. Yes. So I'm going to have concentration on the y, and I'm going to have time on the x. Where is my NO and O2 going to start out? 0. Because NO and O2, do I have any at the beginning of this reaction? No. So I'm going to draw one line here, and I'm going to draw one line here. Which one is NO and which one is O2? Because they're different. Yeah, why? Because you're making double the amount of NO compared to O2. Does that make sense? Okay, so this is NO, and this is O2. And then what's going to start out up here? Because I'm going to start out with what? I have NO2 to start, and that should look how compared to NO? Almost the exact opposite, right? That's actually pretty dang good. That's pretty dang good the way I drew that. So this is my NO2. Eventually, do you see how all of these become parallel at the end? That's equilibrium. But that's next chapter. It's snowing so hard. Look at that. I love it. Okay. So. Okay, literally the radar has nothing on. I've never seen anything like it this morning. There's nothing on the radar. I think the trough is just coming through and it's disturbing enough of the upper level, like it's just making it snow. That was a lot of meteorological terms. I just love the weather. So anyways. I want to teach a class called Earth's Atmosphere and Weather. I think it'd be so much fun as a semester elective.
I would take it. I just want to be a weatherman.
Yeah. And then we would actually like co-op with video announcements, and we would do a real weather segment. I know.
Have you brought this? You should even like.
I haven't yet.
We need to do that to like, because we have something good on.
Reverend Science Club is next Wednesday, by the way.
Okay, I was gonna ask him.
I bought real hydrogen peroxide. We're gonna do for real elephant toothpaste where it should like hit the ceiling and go crazy. I've never done that
I'll
before.
get some good videos from you.
Yes, I know. Okay, so the basis of speed or rate is based on what's called the collision theory. And what is a collision?
Two things,
Yeah, and guess what things we are talking about? Molecules. Yes, particles. So, collision theory tells that a reaction will only take place if three conditions are met. Did you know that sorry, my mind is everywhere right now. There's a lot of high school basketball games that have like canceled Friday because no one's going to go.
Why?
OSU. Yeah. So people are like changing their high school games from earlier because no one's going to come. They're not going to make any money.
Wait, what time is the game?
7?
7.
Is it a 7?
they're playing Texas.
Texas. Yeah. Is it? It's at a bowl.
They might have to move it.
Why?
because Texas is gonna get a huge snow.
Oh, because they're going to
Yeah,
get.
but Texas won't know how to act.
But if Texas gets 5 inches of snow, that is literally the apocalypse for them. Like, I'm serious.
Remember a couple of years ago when like Dallas froze over?
Yeah, and then they couldn't get any heat from the pipes.
We have some really close friends.
Yeah.
That actually goes in Dallas.
Yeah.
He's, like, he grew up in like Minnesota. Or something.
Yeah.
So for no reason he had like a snowplow.
6:30. Yeah, that's the early game. Yeah.
That is,
Central?
So 7
In Texas.
So 7:30 us. Yeah.
Yeah, but since that, they might have to move it somewhere for us.
Okay. Is it outside?
It's like, but
not.
there's so much snow they can't
I
get.
can't get there. Yeah. All right. Number one. The reactants have to do what? Don't overthink this. Yes. The reactants come into contact. I can tell we're already way behind the way I've been doing this, but that's okay. I've just been all over the place. With each other. Yeah, it's fine. We do what we want. You're right. 2/3. In other words, they have to collide. Ooh, wow. Number 2, the reaction occurs at a certain minimal energy. Called what? Think back to biology. Activation energy. Yes. Called activation energy. You will see that as big E, little a, or E-act. So E-act, big E, little a, or just like E-act. Number 3, the collision. The collision has correct, this is kind of weird, molecular, because we said we're talking about molecules, orientation. What does that mean? ... That means the reactants must hit the products, not in like a mean way, okay? All right? In the correct 3D orientation. So, I don't know. So, I'll try to do this on the screen. So, here is my reactant, right? Here is my products. Yes? If they hit like this, oh shit. I literally accidentally made it work, right? If they hit like this, are they going to do anything? No. But if they hit like this, are they going to do something? Yes, that's what I accidentally did. That. I wasn't even trying to make it. Whatever. Dang it. Ugh, too coordinated. All right. If reactants don't collide, so they don't hit, or they don't have the energy higher than the activation energy, guess what? Yeah, nothing happens. Nothing happens. So, all reactions take place in a series of elementary, I really pronounced that T, elementary steps. You guys remember Hess's law? Yeah? Okay. Ah, yes. So we're not going to be doing Hess's law, but this is going to explain Hess's law better. So if I have potential energy and I have time, you will see something like this. It goes like this. There's like a hump. right? And then it goes down like this. Yes? We've looked at these before. Yes? We've done this before. Here's my reactants. Here are my products. I know that the difference between my reactants and products, right, would be what? That's my what? My delta H. Yep. That's my delta H, my heat of enthalpy. And then this hump I have to get over is my what? Activation energy. That's my EA. That's my EA, my activation energy. So these steps can fall into one of three categories or three molecularities. Isn't that a fancy word? You did not expect to write that today. Molecularities. But all successful. Is that two C's or one? Two C's, two S's? All successful collisions are subject to correct orientation. First type. First type is unimolecular. And you're going to probably know what this is. Unimolecular, any guesses of what that means? Yes, a single species. A single species reacts to form products. A single species reacts to form products when a rearrangement occurs. Rearrangement occurs. And this would also be called, in parentheses, first order. So we're going to be determining the order of reactions. Example, ozone could break into oxygen and oxygen. You don't usually see monatomic oxygen, but ozone can do this. It's really weird to see monatomic oxygen. I also just feel very satisfied that I said molecularities and monatomic today. So, I know, troughs and disturbances, man, what a great day. Lucy, I hope you're having a great time on your cruise and you had a great time when you see these notes. Yes. I hope Mickey Mouse is great, yes. Oh, and Maddie, we miss you too. Anyone else gone? Okay. All right. The second type, any guesses? Bimolecular. I know you would think it's di, but it's bimolecular. So bimolecular is, guess how many species? Two species colliding. Two species colliding. Guess what order this is?
Second.
Yes, you're a genius. Second order. So this would be, an example would be NO plus O, let's keep it with ozone, O3. That would give me, we don't really care about the products, but that would give me NO2 plus O2. And that's not balanced, that's fine. We don't care. Third one, guesses. Trimolecular. Trimolecular. Every time I see you, Danny, and your hair, it's just like boom.
Sometimes I look in the mirror.
I know. Sometimes you will hear this as termolecular, not turd. Termolecular. All right? That's three species colliding. And this is not going to be what you think. Okay? Because here's your example. It's going to be 2NO plus O2 yields 2NO2. Do you see it? You would agree that there's two NOs, right? And one O2. So I have 2 plus 1. So it doesn't have to be three different things. You just have to have three total. And one could be the same.
Is it also like third order?
Yes, this is third order. But that doesn't really exist. So you can write third order. But if you want to, you can write it. Flip the page. Can't believe Lucy's on a Disney cruise right now. And it's snowing. I'm guessing somewhere warm.
Well, you can go on Disney.
They left Florida and they went to like the Bahamas.
Ah. So Eastern Caribbean.
It's not even
They
okay.
did.
Eastern Caribbean.
Are you doesn't even know when she's coming back.
I think
All right. The fewer molecules involved in the elementary reaction, the more likely it is that the collisions will be in the correct orientation.
Why is that?
Why? Well, think about it. If I have just one molecule, right, it's going to happen. But if I have two molecules, it's going to be harder for them to hit. Once you have three, then it gets, I don't even have three hands, right? That basically shows it, yeah. Yeah, I don't have three hands. So, this means that increasing molecularity, now we've said it twice, will decrease the chance of correctly oriented collisions. This is why trimolecular reactions are very rare. Trimolecular reactions are very rare. So, in all situations, if concentration, and how do we write concentration instead of words? What do we use? Brackets. If concentration of reactants is increased, think about that, there will be a greater chance of correct energy and correct orientations. Why? More concentration is more particles, right? More chance for them to get together. I don't know why it's harder for me to like look at this and do this than that first time when I was just like, see?
That's why we solved like percent.
Yes, you got it. You got it. Once you string together a series of elementary steps, the reaction becomes much more complicated. But the more complex reaction is just a series of simple ones that we call elementary steps. So that's going to be your step 1, 2, and 3, maybe 4. So here's a complex multi-step reaction. Look how complex that is. Can you guys see that? Not only, all right, how many activation energies does this have? It has 2. Notice that there is an intermediate. So circle that. An intermediate is something that pops up in the middle of a reaction and then is immediately used up in the next step. So an intermediate shows up at the end of one reaction, and then the second step, it's immediately used up. I'm going to show you that in a second. Cool? Flip it. Flip it. So we've kind of talked about this, but factors influencing reaction rates. Number 1 is concentration. Number 1 is concentration. We know increasing the reactant's concentration will increase. I don't know why I did an arrow there and then I wrote an increase there, but it did. Odds of what? Collisions. Love it. Will increase the odds of collisions. That's number 1. Number 2, temperature. Temperature is the measure of the average kinetic energy of a substance. The higher the temperature, the faster the particles are moving. The higher odds of them colliding. Here is what? What graph? Maxwell-Boltzmann, yes. This is the Maxwell-Boltzmann, right? I know, I even gave you that MB. So remember what they're showing here. Here's my number of particles. Yes. Here's my energy of the particles. If it's cooler, my hump is over here to the left, right? Yes, I can. If it's warmer, my hump is lower and to the right. But what do I have? I have more particles, right, at that energy I need. So this kind of applies the Maxwell-Boltzmann one more step. Yes. So, number 1, concentration. Number 2, temperature. Number 3, what else? Solid particle size. How am I going to change that? How am I going to make this happen faster with solid particles?
Heat it up.
What?
Heat it up.
I already heated here. What am I going to increase? What? Not pressure. I want it to have a larger volume. In order to make it have a larger volume, I have to increase the what? What? Surface area. Yeah, crush it. I'm going to increase the surface area. That way, I've got more particles touching, right? If I have a sugar cube, only the outside of the sugar cube is touching the water. If I crush it, it's going to dissolve much faster. Also, not a chemical change, but you get it. Okay. Flip it. We're flying. We've really picked up steam. 4, I know. I knew we'd get it back. Catalyst. But that Mountain Dew is in the back of my head. And I brought pickle chips. You guys ever have pickle chips from like, who makes it?
Lay's?
Not Lay's.
Ruffles.
Not Ruffles. It's not Kerr's. The other one. It's Ripple. They're like Ripple pickle chips.
Yeah.
What? Utz. Yes. Oh, so good. Utz. Chips. Oh, well, you wouldn't like this then. You wouldn't like this. Guys, my wife never had salt and vinegar chips till last year. What? And she loves them now.
Those are like
Yeah.
top 2 chips.
Emily, if you ever watch this, I just want to let you know that we all still love you. It'd be weird if she did watch that.
Yeah.
What if, like, this is going to be really tragic. I died. And then my YouTube videos are the only stuff left of me in the future. It is tragic, though. And then she, like, went back to, like, hear my voice. I don't know. If that happens, I love you, honey. I love you. Yes. Anyways, Avi and Jovi, I love you too. All right. Yeah, all right. Yes. If something happens to me, let her know. My final message to her. I should leave my will too. My will is for this would be a binding legal thing if it's posted. My will is for Stonky Kong to go back to Mr. Ruff, Dylan Ruff. He lives in Wadsworth, Ohio. For all of my money, investments, everything I own to go to Emily Heller. And then my daughters after that. And for my legacy to live on in all my students. There we go. That's binding. That's binding. That got depressing. Got weird. We'll talk about it more later. Okay.
You saved it. Oh, I know that.
Are substances that... Oh, sorry. Back to catalyst. I was like, what are we talking about? Catalyst. All right. I should probably...
Oh.
I'm just laughing at myself. Like, it's so... It's everywhere right now. Catalysts are substances that increase... Yes. The rate of reaction while remaining chemically unchanged. So catalysts don't change. They're part of the reaction, but they don't do anything. They don't interact. Do you guys remember doing freshman year, maybe even junior year in CP Chem, the reaction with yeast? Right? So you put the yeast into the hydrogen peroxide, right? And then you lit the splint on fire, you put it back in, the splint relit, yes. The yeast was the catalyst, right? The H2O2 would have broken up into O2 and H2O eventually, but it would have taken like 2 weeks. The yeast just made it happen fast. Didn't affect it. So you still have O2 and H2O, just at a quicker pace. Like a what? Should smell like a brewery.
Yeah.
Well, it could smell like either, really.
I mean, they kind of go.
Yeah, true.
Yeah.
Yeah.
They're like two different.
So, catalyst, lower the what? Activation energy, you got it.
Do you have a sourdough starter? That like is like alive and
My mom does.
Catalyst, lower the activation energy. This does not change delta H, right? Delta H is not changing. Agreed? But what is changing is the hump. The hump is getting lower. You guys good with that? Yes, less hump. Yes. Active catalyst equals less hump. I like that. That should go on the t-shirt. It's a good one. More specifically, catalysts cause more effective, not reactions, collisions. More effective collisions and or provide a reaction path with a lower activation energy. So there are several different types of catalysts. Type number 1, acid-base. This is where a reactant, guys, I have a real will. I'm just letting you know, okay? Don't worry about it, okay? I have an actual will. What's that?
Are we involved in the will?
Yeah.
No,
What?
but I do hope my legacy would live on in you, somehow.
Your love and adoration.
Yes.
You don't even get the balloons.
Lucy can have the balloons
Oh, the birthday balloon is.
because she made them. It died.
I think that should get two.
Rough doesn't
Because
want-
yeah, if Ref doesn't want Stompy, can we fight over?
If Ruff doesn't want Stonky, you guys can. If Dylan Ruff does not want Stonky Kong, my AP Chem 4th period, 2025, can rock, paper, scissors tournament to see who gets Stonky Kong.
We should like have it like.
The Stonky's girl goes to my daughters. They can fight over that.
Wait,
Wait,
can I call the
doesn't
candy store?
Stonky keep her?
What? You're right. They are together, so they stay together.
You know what? That's
So either Mr. Ruff gets Stonky's. I don't know. We need to name her. Stonk's girl. Yeah. Oh, Stonkette. Yes. Stonkette also goes to Mr. Dylan Ruff. All right. Guys, here's the thing. We're all eventually going to die someday, okay?
okay. Stop.
I don't know why. Sometimes you just face your mortality in different ways.
You know what makes me
I don't know. I don't know. What? I don't know.
Is this a foreshadowing?
You should just talk about death occasionally, all right? What?
She finds like a secret.
No.
This is very bad.
What? Interstellar, yes. Yeah.
This is very bad foreshadowing. You can talk about death for like 10 minutes.
It's fine. It's all good.
I like how as soon as the locked in, it was like.
Oh, we unlocked as soon as I know. All right. Acid base. Let's fly through these next couple pages. We'll either lose or gain a what? A proton. Right? You guys agree that a proton is essentially just a hydrogen ion, right? Yes. Forming a new intermediate. I'm going to show you what an intermediate is in a chemical equation soon. And as a result, the reaction is changed. The reaction rate is changed. In fact, it should be faster. In a reaction mechanism containing a catalyst, the concentration of the catalyst is unchanged. Remember, the catalyst isn't part of it. It just makes it faster. However, the catalyst will sometimes be consumed in the rate determining step. Underline that. The rate determining step, RDS, is the most important step in these reactions. Only to be reformed in a later step in the mechanism. Flip the page.
Is that increase?
That's just brackets. Just concentration. Just concentration. Just concentration. Okay. In organic chemistry, all right, these are good examples. These are good examples to do. A specific class of compound called a ketone can be converted to another class of compound called an enol with a simple rearrangement. So here's a ketone going to an enol. A ketone is basically just a C double bond in the middle. Okay, you don't have to know this. Okay, but that's what it will look like. It's found that the rate of this conversion can be changed by the introduction of another substance. So the chemical equation showing two examples of the introduction of such substances are given below. H3O plus, have we talked about this? We have. What is that? H3O plus is, oh, maybe we haven't. It's hydronium. We're going to talk about that more. It is heavy water because essentially you're gaining an H from H2O is taking on an H. So H3O plus is hydronium. H3O plus is, what's the question?
Can you forget? Is it like the same as water, or is it like liquid?
It's the acidic version of water.
So probably don't.
So, but water is just slightly acidic. I'm not sure. So,
Maybe it was a short. I'm pretty sure he did.
H3O plus here And then, so H3O plus is my catalyst. Notice how I start and I end with the catalyst. Do you guys see that? What's the catalyst on this one? Excuse me, in this one? Hydroxide. So, it's found that H3O plus and OH both increase. I went ahead of myself. So the role of these are what? Catalyst. So, what feature of the equations shown above support my answers? I'm so sorry. It is you start and end with it. So, you start and end with it. You start and end with it. I started with H3O plus, I ended with H3O plus. What?
I'm starving.
I am too. A surface catalyst, so that was acid base. A surface catalyst is usually a metal, which is usually solid, right? Reacting with a non-metal, which a lot of the times is a gas, or the catalyst is in a different phase than the reactants. So if the reactants is metal, the catalyst is going to be a non-metal. So for example, hydrogen and nitrogen gas absorbed onto metal, and the covalent bonds are weakened, producing highly reactive, this is crazy, singular H and N atom intermediates. Once again, intermediates, monatomic H and monatomic N, which we know are diatomics. So those are super reactive. They're intermediates. Now, because they're intermediates, what are these pretty much immediately going to do? Pick up another, H is going to pick up another what? H, and N's going to pick up another N. And those intermediates are going to be there, and they're going to immediately be gone. They're going to be used up in the next step. Those then, see here it is, react very quickly to form NH3, which is called the Haber process. Putting gases onto a metal surface also increases their concentration, causing more collisions. Yes. Causing more collisions. Kevin, are you senior? Are you senior?
No, I'm freshman.
You just look older since like you just look older since winter break. You've matured more. I don't know. It's the hair.
Really bad.
Yeah, what's different about it?
No, I just haven't gotten here.
Oh, okay.
That's the difference.
All right. Did you get taller? I think you might have. Oh, growth spurt. Catalytic converters. Who's ever heard of a catalytic converter? Where do you find them? On a car. That's what they steal. Here's why. Here's why. Contain transition metal catalyst embedded on a solid phase support. Sorry, the solid phase. I'm dehydrated.
Do you just, is that still the water bottle or like the water bottle when you drink it?
I feel like I would have
Yeah, I thought we did.
Oh, it's gonna work. It's gonna work.
I still don't believe that it actually works.
Just wait.
Oh, the water bottle.
It's gonna light up. If this doesn't work again, I will be so disappointed.
I don't think it's real.
I've actually
No, it's
not
not.
It's working. I've seen it work. I've seen it work.
This whole bottom band lights up. Hold on, let me check the app.
You got a water bottle
Yeah.
there. This
Yeah.
is space shy. That's cool.
I've seen it. I've seen it.
You should bring another water bottle.
Oh,
What happened?
I got a new phone and it logged me out.
So all the water you drink.
Also, my Apple Watch doesn't work with my phone anymore.
The AT&T.
Wait, how?
What's that? This is an Apple Watch Series 4. So it's real old.
What series are they on then?
No wonder
What's
they're
that?
out. Like,
What series is like the current one?
I'm not sure.
Guys, remember phones when came out?
Yeah, this isn't even synced with my new phone.
How convenient that.
That's why. I know. It says no bottle. Wow.
They even skipped
Remember like the
Sorry. I promise you'll get to see it someday. I love how Danny just like flexes a sip on his water bottle that doesn't light up to show me it's the same as mine right now.
It doesn't work.
I know, you're right.
I swear there's no lights.
All right. Back to catalytic converters. So, Back here, the solid phase catalyst comes into contact with gases from the exhaust, right? Which those gases are not good. Yes. Exhaust stream, increasing the rate of reaction to form less toxic products from the pollutants in the exhaust stream, such as carbon monoxide and unburnt fuel. So, and what are in those catalytic converters, Nathan? You were just saying. What's in the catalytic converters? What metals?
Oh, platinum.
Platinum, silver. And that's why people steal them off your car. Do you need a catalytic converter on your car? No, not technically. It'll run the same, it just doesn't run as clean without it.
Like over like 1970 or something, not have them.
Probably. Yeah. Yeah. Wait, your car's still good, right? You didn't,
It's good.
but did you get in a wreck?
No,
That was someone else.
Almost.
I almost did.
Almost. Yeah.
Hey, we should go drifting again today.
That should be the first. What if the first thing I did when I can drive
I
again?
thought about that the other day.
All right, the first time I go driving, I go into a parking lot and I just start doing donuts, and then I just ran my car into a telephone pole.
Wait, you used to go to that same street that you drove as a yard.
I'm not gonna die from
I'm
that.
told Grace Church.
I guess it depends if it's driver's side or not. What?
Go in that, remember when you crashed in the yard?
Oh, down on Woodland. Yeah. Reenact it.
I forgot yesterday.
Yeah.
Actually hit the house this time.
No. Here's the thing. I was a teenager then, so like it'd be way worse as an actual adult. Let's be serious. Yeah, you don't bounce back from
Just
that.
that, like,
And then I would probably literally lose my license. So, okay,
Be on the bike forever.
let's keep going. Forever. Guys, I rode my bike to school yesterday in the snow. Oh, it's freezing. There was one point when the snow was like this deep on the sidewalk, and I had to turn it to like 5 to like get through it on my e-bike. It was crazy, but it worked. Will. What? Hold on. I cannot hear what Will's saying. No, because Nathan needs a test to take the next one.
Come on, Nate.
So he's taking that tomorrow morning. We'll go over that test tomorrow. Okay. All right. If you have a transition metal, let's lock. That react with monomers, which are long chains, that's how you get plastic. Okay, moving on. Not important for us, but just wanted to put it there. Enzymes. Here's your biology. Here's your biology. These are complex proteins. I know, exactly. Because I don't like biology. All right. That act as biological catalysts. Many times thought as a lock and key process. Have you guys read Fourth Wing? Yeah, you have, Audrey? Fourth Wing, it's like a fantasy book about dragons and stuff. It's a series. No? Okay.
I feel like this is
Is it the one with like the white and gold color? Or am I making it up?
I don't know. Okay. Anyways. This should not say that, this, I don't know. This accelerates the reaction by connecting to the reactants and either aligning or causing the reactants to react with a lower activation energy. So here's my enzyme, here's my substrate. You guys remember this from biology, right? Yeah. You like eat it, and then it breaks off, and then you get whatever you want to try to get.
It's like ATP.
Yes. Yeah. With Mr. Conrad? Yeah.
Rob didn't do that.
Wow.
There's a board that's hanging out that has my signature on it. Because I was the first.
Nice. Okay. That's kind of like a weird little break. We're done talking about catalysts. Okay? The sequence. So here we go. Let's get into the actual math now. The sequence of elementary steps that make up a chemical reaction. That make up a chemical reaction is known as the mechanism. This paragraph is really important. So put a star by this paragraph. Each step will be either fast or slow. There's no medium. Okay? But the overall rate of the reaction is only dependent on the slow step. Where are my cross-country runners? Cross-country team. Isn't your team score kind of only based on the slowest person? In a way. But the slowest person kind of brings you down, right? No? Okay, bad example.
All right, so
And then the
swimming.
fastest person brings you up just.
Yes, swimming. That's a better example, right? If it's a relay, right? Your slowest person, right? Your slowest person is probably going to be like the first one to go, right? Is that how they do it?
Oh, it's usually like
Second or third leg?
second or
Okay. But your fastest person is going to be the closer. No?
Either person.
First or, okay. But your slowest person is going to be your determining, it's going to be your rate determining person, right? Same thing here. So this step is known, as I alluded to earlier, the rate determining swimmer. Just kidding, step. The rate determining step, or RDS. So here's the equation. Here's the equation. Rate equals K. That's what K is. It's a constant. In fact, it's the rate constant.
What is this, the other K?
It's another K. There's so many Ks.
So many letters in there.
So we've got to, this is just another K. There's more Ks coming next chapter. We haven't talked about KW,
How
okay?
do you keep them?
All we use are K's and B's.
They're just a bunch of Ks. Ks are constants. That's what we have to know.
K's, B's, and K's, B's.
Oh, look, the first of many Ks. Here we go. X, Y, and Z are the orders with respect to the concentrations of the reactants A, B, and C. The order with respect to a given reactant is the power which the concentration, I think I said concentration like 12 times today, of that reactant is raised to in the rate equation. The overall, so the overall order of the reaction is the sum of the individual orders. So if this was a 1, and a 1, the overall order would be what? 3. It'd be 3.
So the power still matters.
They're not super important. You're adding. Yes, because when you multiply exponents, you add them, right? Yes. Rates are strictly based on reactants. That's really important. Put a star by here. It's only on what you start with. You will never see products in the rate equation. In the rate equation. Flip it. Flip it. We're kind of cooking a little bit here. Okay? Rates can only be determined experimentally. So that means you have to do an experiment, which we are going to do on Friday, using, what's that? It's going to be Friday afternoon. We'll be fine.
It's gonna snow right after.
Yes.
Well, then they can't split. So
What if you get snowed in the school?
Not till like later Friday afternoon. Using coefficients of the balanced equation will not deduce anything. So you can't just look at the coefficients and then assume it's some rate. Therefore, orders must be determined experimentally. But, there's the but. All right, there's always a but. It is possible to get orders from the stoich of the balanced equation if you know what? If you know it is the rate determining step. And then the coefficient in the slow step, and you'll see this in a second, becomes the power that concentration of the substance is raised to in the rate equation. I'm going to show that in a second. Note, rate constant units get weird. They get weird. All right? Wacky, whatever you want to put there. A reactant that has a 0 effect rate on the rate is said to have an order of what? 0. Good job. Because any number raised to 0 is what? 1. So if you're raising something to the power of 1, are you changing it? No. So therefore, it can be omitted. O-M-M-I-T. I think that's omitted. I don't know. Whatever you guys want to write. As long as you know what it means. Okay. Omitted from the rate equation. Note, orders can be fractional. So an example would be 1/2. I know, mind blown. Note, in all valid rate laws, the sum of the individual steps must add up. Note, intermediates. When I start writing notes, it's just like random things I needed to say, are formed in one step, but then are used up. We talked about this. They're used up in a later step. When intermediate is found in the rate determining step, it is usually replaced. That's really important. It's usually replaced. If a substance is present at both the start and at the end, what is it? It's a catalyst. It is a catalyst. So, take a look at the decomposition of hydrogen peroxide. So here's a decomposition of hydrogen peroxide. Let me zoom in a little bit more. So I've got hydrogen peroxide plus iodine ion gives me water plus, looks like a weird iodate ion. Then that iodate ion is used up to make, with hydrogen peroxide again, to make water, iodine ion, and oxygen. My overall equation, right, if I would like add these up, cancel out stuff on both sides, yes, would be 2H2O2 gives me 2H2O plus O2. What is the catalyst in this equation?
The iodine.
How do you know?
Because it's in the first.
Because you start with it and you end with it. Would you read that you start with I minus and you end with I minus?
Yes.
What is the intermediate?
H2O.
No, the IO minus. Because the IO minus is formed in the products of the first step and then immediately used up in the reactants of the next step. That's an intermediate. Does that make sense? Just give me a little head nod if that makes sense. Last note. A reaction that is second order has a rate equation of K, A times B, because what's 1 plus 1? Yeah. Could be carried out with a large concentration of one reactant compared to the other. When this happens, the reactant with the large concentration will basically be constant. Think about that. Why? Because its concentration will change so little, right? Compared to the amount of the other concentration changes. So if B is really, really, really big compared to A, you could really just rewrite the rate law as rate equals Ka, right? Because A is changing so much. And it's a pseudo first order reaction, but you rewrite the rate law as rate equals Ka. Oh, sorry. But you probably won't see that. I just wanted to throw that in there. So if you have one that's super, super, super big, so if you have like A is like 1,000 and then like B is like 0.002, it's really mostly based on A. Okay? So, identify the catalyst and the intermediate in the mechanism below. Do that now. Why don't we square the catalyst and circle the intermediate? Joe, what did you square?
My square V2.
V2O5, yes, is the catalyst. Because I start with it and I end with it. What'd you circle, Haley? W. V2O4 is the intermediate. That's a good place to stop for the day. Good place to stop for the day.